This is ST536, Masters of Science for Teachers. I'm Rob Hepler, and today we're going to talk about database systems, or DBMS, as database management systems. There's the contact information. And of course, databases are what we all live with. It's the engine for the web. It pays for the web. It pays for those web pages you look at. It's how Amazon makes its profit. I know Amazon sends products to your home, which you paid for, and they make profit on that, but their real strength is their data. They know who you are, what your likes are. They offer you things you might like. They know where you live. They can find the cheapest warehouse to ship your things from based on the data. But there's just a lot of things going on in the background. But the ultimate in data, of course, is websites or companies like Google. Google never charges you a dime for anything. And yet they're one of the most highly capitalized corporations in the world. They have an awful lot of cash. How do they make that money? Data, data, data. They capture all your behavior in data, as much of your demographics information as they can get, as much of your email contacts as they can get. They analyze it. They use mathematicians. They do what we call data analytics today. It used to be called data mining. A little bit different, but data analytics allows them to paint pictures, focus, and sell information, in a sense, to vendors, to other companies. And the reason they can do that is because their database allows them to tell the people they're trying to sell the advertising to, we can target your advertising at people that are more likely to respond to your advertising. They can also track it and prove it to them. Last month, you paid us X amount of dollars to put this ad on people that we thought would click on it. And we can prove to you that X percentage of people that you showed your ad to clicked through, it's called, to your website or whatever it is you wanted them to click through. So it's all about databases. And we're all comfortable with data. We use it all the time. But what we're going to talk about here is how we put structure to the data and how we make information out of it. A database, of course, here's the definition from the textbook. Collection of data organized and so forth. You can see that. So the idea is we have a wall around this data. That's your database. It's comprised of data. And then we get information out of it. So we have input. We talked about this before, process, and output. The data is processed and turned into information. One of the keys to database design, and I'm going to use that word a lot, design and systems analysis, structured analysis approach to information systems, is that the information often is not stored in the database because there's no reason to store a lot of information if you can compute it from the data. In other words, the total for your invoice at Amazon, it will not be stored in the Amazon database. That doesn't make sense. They store each line item in your order. If they want the total, they'll total it up. It sounds like, it may seem to you like maybe they should keep the total there, it's quicker. It isn't. Because what if you add another item? Or what if the price changes? All of a sudden they have to update the total again. So it's better, if you can, to not store information. Now there are exceptions like the images, the video, the audio, and whole documents, but those are processed. You can think of this video we're looking at right now, gets stored on our Adobe Connect server. The database on that server is very small, even though we have about 8 years now, something like that, 7 years, 6 years, of recordings, 100 hours a week recordings on that database. All the database stores is pointers, and we'll talk about that. What that is an address to the recordings themselves. Why store the recordings in the database? So these are some terms that we're going to be using. And you've all been through this, so it's a good example. when you come to the university the first time, and perhaps you don't come here if you're a distance student, but when you go to the website or when you talk to somebody on the phone or when you fill out a form, your data has to get entered by someone, actually here, which then goes to a disk somewhere and eventually goes to a database. Oh, the database is here, I'm sorry. And at some future point, your data is extracted from that database, and the idea behind a database is it's accessible from anywhere. And there's only one copy of your information. That's the crucial part of this. Accessible and only one copy. And of course, what we show here is there's different uses for your data. You can print your ID card and so forth. You get the idea. The database is the core right here, and it's accessed from all over. So you can add it, modify it, or delete it. It's pretty much all you can do to your data. So DBMS is the term that's used, Database Management System. Does these things, and here's the functions again. Add, modify, delete. Those are the only functions you can do, if you think about it. And as you get information, you might want to do these things. You might want the information in a certain order. And of course, you want to retrieve the information. So that's what the DBMS does for you. The term data integrity identifies, as it says here, the quality of the data. What does that mean? Well, your data has to be accurate, essentially, and we'll go through in a little finer detail in a minute here, but you have to have a high level of data integrity. People have to be able to trust it, which means you have to have security, and you have to have audits, and you have to have human beings reviewing the data to make sure it's accurate. Because you can, sometimes you don't have, as it says here, GIGO, garbage in, garbage out. If you don't have someone that knows what to expect from the computer system, it could go haywire, and you could think you have good data and you don't. So on some level, there always has to be human intervention or human review of any information coming out of the computer. A programmer could change the way your check is totaled, and if there isn't a human being, in this case, when you get your check, it's going to be you reviewing that output. It could just continue to be wrong. So there has to be a human intervention at some point, and to make that easy, we have accounting systems, and we're going to talk about that with in the lecture on applications programs. So the idea is you have to have a lot of integrity or people won't trust it, and the whole process goes away. You have to have that, and you got to have good data coming in. So in order to do that, we're going to talk about some processes to make sure that we have a high level of data integrity. And here are some of the characteristics of a good database. It has to be accurate. When you're building the database and testing it the first time, if you have an old system, you will compare the new system to the old system. That's called parallel testing. And you'll make sure the output from each system is the same, or if the new system's more accurate, you have to explain why it's a little different than the old system. And if you can explain it, not you as I always think of myself as the database designer. I've done a lot of that work in systems analysis. The end user of the information tells you, and they have to understand that it's accurate. Well, verifiable, that's just what I was talking about a minute ago. You have to have a way to be able to tell. How do I know this is correct? Well, during testing, of course, you can compare it to the old system. But when the old system is gone, because that's why you developed a new system, and the old system could be a manual process, by the way. It could be automating a manual process. Well, when that goes away, you have to have reports, procedures that allow human beings to continue to check. Now, the computer can do a lot of internal checking, but you have to be able to verify it to the satisfaction of the end users. In many cases, that's you, your monthly bills, your statements, and so forth. Other times, it's the accounting people at the business or the salespeople, whatever it is, and they'll have to have a way, reports, error reports, audit reports, month-end processing, accounting reports, and so forth. It has to be timely. Well, that kind of makes sense when you think about it. What that means is it has to be available when you need it to be available. Customer walks into a library and wants to know and wants to change their address. Well, you have to be able to pull it up and change it right then. or have a process for that. But the point is, the most valuable databases are timely. A person is delivering goods to a 7-Eleven store, and they want to know how many they need to put on the shelf. Well, they can find out now. They can tell them with real-time data how many are sold, and the person can then, when they load the truck, know how many to put on the truck and how many they need to deliver once they get to each location. So they can load the truck in an organized manner. That's what we're talking about. You have to be able to have information when you need it. It's great that it's accurate, verifiable. If you can't get it when you need it, it isn't worth anything. It has to be organized. And what that means is you have to be clear who owns what data and who can change what data, who can read what data. And it has to be organized in a manner that you can get the information you want out of it. There's a real knack to that. You just don't throw some files, some data into a file and work from that. Accessible, well, that means it has to be accessible from just about anywhere you want it to be accessible. If I wrote a system once to weigh cement trucks, we weighed them when they came in, we weighed them when they left, and on the bill of lading, which is the piece of paper that we used at that time, it would say what kind of cement it was so we'd know what to charge them. And I was able to access that information on the sales database inside the building, and that would automatically register and bill the customer based on information entered at the weighing station. In addition, of course, the vice presidents, the salespeople, the plant making the cement could access that information, know how much was sold, how much they needed to make, and so forth and so on. Has to be accessible by the people that need to access it, including the customer in many cases. Useful, that seems silly. Of course it's useful. Well, sometimes databases are not very useful because they don't show you the information you need to see in the proper order. And of course it has to be able to pay for itself. I want to show you a picture here, if I can find it. Yeah, take a look at this picture. This is actually Trinity Library in Dublin. The Book of Kells is a very famous handwritten book, history, and it resides here. If you've ever been to Dublin, you probably went to see the Book of Kells. This is the library. Look at all the books here. Look at this. Think about a library for a second. I want you to think about that in terms of how do you organize a library? How do you do that? Well, you need to think about how do I need to retrieve these books? I could put them in there randomly, and I think they did that often at monasteries, the monks, and there was just Father John that knew where all the books were. They didn't do a whole lot of organizing, and that's why research often took so long. It was a manual process of going through. But as we move forward, people got the idea that we can organize these books somehow. So you could store them by title. In other words, sort them and put them in the library by title. Of course, that means you have to know the title, what you're looking for. And if you get new books, you fill up all the shelves and you get new books, and you have to put something in here, you have to move all the books behind it to get them back in order. That doesn't make sense, really. And what if somebody wants to have all the books you have on genetics? Well, I don't know. Do you know the titles? Well, then maybe we could do it by author. At least I know what area the author's in. Well, not necessarily. Authors may be in more than one area. You get the idea. So we need to design a structure to organize these books so we can get at them. And an Englishman by the name of Dewey, I can't remember his first name, was it Robert? Anyhow, developed the Dewey Decimal System. Here's a quick slide of it. And he just categorized the books. We could quibble back and forth about maybe some of the categories he put in here, but at this point, who cares? It's just a way to structure books. So every book in a library has a Dewey Decimal number on it. And we've got the general categories, generalities, philosophy, and psychology. Interesting, they put those together. In his time, philosophy and psychology were thought of as about the same. Psychology really wasn't a science, considered a science perhaps when he did this. But in any case, and then the dots below philosophy and psychology each get their own numbers, and there's further breakdowns. So you have 100.105.76.5, and then the last number identifies the book itself, and so forth. Okay, now I have a way to store the books on the shelves. that is organized in kind of an interesting way. It's by subject. But then, like earlier, we were talking about, what if somebody comes in and says, well, I'm not sure what subject the author is in. So what we developed at libraries were card systems. Probably many of you don't even remember them. We don't use them anymore. But you could look at the card system, and each book had at least 3 probably cards, one by title, one by author, and one by subject. And you could then go in and ask any one of those 3, and the cards themselves were sorted. There's 3 different catalogs, one for title, author, and subject. And then you went to whatever one you knew, and you looked up, and they were in alphabetical order, the cards themselves were. And then you would find the number, and then you would go to the bookshelves and go to that section of the library and find your book. What they've done is removed, if you will, the information you need from the books. They put them on cards, so you didn't have to wander every aisle in the library to find your book. The cards told you exactly where they were. They're separating, so the cards are something we call metadata. And that's the basic concept behind databases. We don't want to search all the data to find what we're looking for. Remember, Facebook has, I think now, 750 million people, customers. That's, you know, more than most countries. I mean, it's a lot of people. So you don't want to search through all of those to find, when you log into Facebook with your, email and password, they want to get that quickly and show it to you. You don't want to wait 20 minutes while the computer searches through 750 million records. So we separate your login information from your data, and we have that in a separate file called an index, or there's a pointer system. That's the same idea we use in the libraries. The libraries work the same way, except they have databases now, which means you don't have to resort the cards every time you get new books. You just throw them into the database, and the DBMS, Database Management System, updates the card file or the index file automatically. So you just add the new books, in whatever fields you want to search the database on, the DBMS creates an entry in what we call an index or a hierarchical structure file. Metadata, real data. That's the basic concept here. There's a hierarchy of data as well. Top level, if you will, is the database. And then below that, there's files. Student file, instructor file, schedule of classes file, and so forth. You can see it there. And we break that down even further into fields. The files have many records. The records have many fields. The fields are made up of many characters. And this is where you start with designing a database. You start at this end and work this way. And you ask the people that use the data. You find, if you don't have a database, you find if they have paperwork they're filling out manually, you get all the forms. And you start documenting what's on the forms, what's being captured. And you work from there. And then you find out who owns the data and so forth. And then you start building your database. This is obvious. A character, we've talked about this before. Remember, we talked about the ASCII character set. A character is 1 byte. My name, with the ASCII word for R, O, B, don't mean anything themselves. But if I put that into a field called first name, now it means something. Not to the computer, but it does to me. That's my first name. You get the idea. And then we take those characters and make a field, which would be a field name. It would be first name. And we have to define a size within limits. We don't have to define an exact size like we used to in databases. Databases now are much more flexible than that. And we define a data type. I don't want to go into that too much, but the practical reasons you use data type is it allows you to edit information when it comes in. If it's your social security number and you type a letter, we can have the program say, no, you mistyped something. So you can edit the data. Remember, you want it to be accurate, so you'll edit the data coming in. Verification, that's called, data verification. There's other reasons, technical reasons. You can store numbers in less space than you can characters. and so forth and so on. So it's also for efficiency reasons. And registers on a computer can do different things with numbers than they can with characters. And if you're going to do math with something, you have to define it as a number and so forth and so on and so forth. So there's other reasons as well. And notice over here, we have two files. Let me move the cursor off of here. And we have some data types. Obviously, these are the field names, right? Here's the file name. Here's the field names. And here's the data types. And this whole thing here is a file. You get the idea. File is made up of a record. Each of these rows, is a record, we would call it, or a row in Excel is a record. And each of the, and then each of those records, I made a mistake here. Let me back up just a second. I didn't say that right. So forget that. Sorry. Each of these is a field. And then inside the field, and inside the file, these are fields. Each field, group of fields, is a record. Many records make up a file. So this is the definition of one record here, okay? Now that's correct. Each of these in this picture is a record, okay? Although they call it a file, it really should say a record. If you had a bunch of these records, you'd have an instructor file. Just to be clear on that. Same thing here. Notice some of these data types. Hyperlink. Well, that allows the program to do different things with that, which of course is to go to the web. Attachment, that means there's just a pointer here. An address on the disk. Go out there and pull that image up and put it on the monitor when we pull this record from the database. Auto number, well, that's an automatic number that gets incremented each time by the database automatically. That's how we assign your 900 numbers, we call them here at Tech. The database automatically gives you a number. And there probably would be in here somewhere your social security number, I'm guessing, but they didn't put it on here. Why? Because the social security number is another way to identify you. If you forget your student number, we have to have a way to identify it, which happens all the time. So your social security number would probably be in this file. Once upon a time in this country, it was illegal to use social security number as a key in a database or even a field, but those times are gone. And you get the idea. We're building from the ground up. Here's some data types. Memo is a field of any length. You don't know how long it's going to be. This is just a yes or no, obviously 0 or 1. You get the idea. An object, as I mentioned earlier, in the Adobe Connect database, all these recordings are objects. The database itself just keeps records, finds ST536 in the database, goes to and has a file called recordings, goes down the recordings to number 6 and says, where is that on the disk? And goes out and plays the flash video for you when you're looking for it. Okay, here's a better picture. A record is a group of related fields, and notice related, that's an important word. Each of these rows is a record, if you want to think about it in those terms. It's interesting, what I see here is these records don't have an identifying field, do they? These columns are the fields. We're so used to Excel, we talk about things in rows and columns these days. And there's no identifying, how would I identify any of these rows for a specific person? You couldn't, could you? Not really. Many people live in Indiana, many people live in Charleston. 54 Lucy Court, well, there could be more than one Lucy Court. Albuquerque has some streets that are names that are repeated. Or you may have moved. All those things are problems. So you need a key, an unchanging primary key, which this doesn't have down here. Okay, just so you're not confused. Then the data file is a collection of all these records. So this whole thing is a data file. And if it helps, a Excel spreadsheet, Lotus is a long time ago, is a file, if you want to picture it that way. Okay, and we've talked about this before, adding, modifying, deleting records. Add records, a little redundant. You understand adding, modifying, and oops, I just hit the wrong key. Hang on. Okay, here we go. Okay, sorry about that. Validation, we talked about this. This is an edit you do on the front end or when the data is coming into the system based when you define each field, you define the data type, and the database will only accept data of that type. Alphanumeric, of course, is anything. Not much of a check you can do there. That means anything. But there is such a thing as a range check. For instance, zip codes have a range. We know they're 5 or 9 digits, but we know there's a lower range beyond, and the post office doesn't use any numbers below a certain number. I don't remember what it is anymore. When I knew, it's probably changed since then anyways. And then there's an upper level too. Zip codes don't, and you can put that check in the programs. And the smartest database is actually you can put that check in the database, even range checks, so the programmer never worries about it. And the database just sends a message back to the program. Consistency, well, that has to do with things like, in order to add a class registration record for you, you must have a student record. Perhaps that's it. Or you could check that today, the day you're registering has to be after your registration date, those kinds of things. Consistency checks. Does it make sense that you're entering the data like this? Make sure everything's included. Check digit, well, that's a way when you enter a social security number, you can do what's called a mathematical algorithm on those 9 digits and come up with a number. And that number, when it's entered, is sent to the database, and then it does the same computation again to make sure that you, so you enter the check digit. The database then forgets that you entered the check digit, computes it again, and compares it. So, and there's other things we can check too. These are just ways to make sure the data is accurate. So just a little bit of background why we use databases. We used to use files. Let me show you an example. That's not it. Although you could think of that as a file. That's not it either. Here it is. Here's a file. This is a text file. And this is how we used to do data. And each department had a list of customers, or whatever it is you had a list of, employees, whatever it was, books, classes, classrooms, furniture, whatever it was. And it was printed out like this, or even kept handwritten in a notebook. In fact, well, so you can kind of see here, this is obviously a last name, first name. And I can tell you what these are, and you can probably figure it out. These are scores for quizzes. Here's this average for the quizzes, and so forth and so on. The record goes off the screen here. I'm not showing you the whole thing. But, so what you see here is each row is a record, right? Each column's a field, and you could label those fields, and you can even give them data types. So this is kind of how we start designing a database. But if we had, imagine Facebook if they were using a file system. 750 million names in some notebook somewhere, and you want to find the person's account number. Well, that's ridiculous, of course. But why is it ridiculous? It's because, number one, as you add new people, you're going to add them at the bottom. Okay, and as the file gets bigger and you want to find, let's say, David Rangel, well, if it's a small file, you can go through and find him. He's right here, pretty easy. But you can't do that in a big file. You can't keep this sorted, because it's already a hard copy, or it's just a regular flat file, we call it, just a text file, which is what this is. So there's all kinds of issues in terms of retrieving the information. How do you modify this thing for darn, it's difficult. Do the columns have to line up? I don't know. What kind of programs are we using? What if I get the columns off? All our reports are wrong then. There's all kinds of issues here. So the database puts structure to this. and allows us to sort things. And remember the idea of a index file and a data file. Talked about that with the library. Let me erase this. All right. So the index file for this data file, let's just say for the sake of argument, we want to search this or retrieve information by last name. So over here we would have, and if we numbered these records, 1, 2, 3, 4, so in a sense it's a row number, but that's an address on disk, let's think of it that way. What we can put in the index is the address, 1, 2, 3, so forth, and then we put the last name, Andrade, Arroyo, and so forth. So now what you've got is an index file when we want to find somebody. And what we can do then after we have this file, we can sort the index file because it's less data to move around, easier to sort. And once it's sorted, we can write algorithms. It's easier to read this file because it's smaller. We can probably fit it into RAM. Don't have to read it off the disk once it's in RAM. For instance, we can also do what's called a binary search. And there's all kinds of techniques we can use on this file that we can't use on a huge data file. So when we add a record up here, we have to add an entry here. We sort this file. And so these are all out of order now. That's okay. But it's in order by last name, and then when we find what we're looking for, we pull that record number and go to that row and retrieve it. That's essentially how a database works. It's much more complicated than that. That's the concept. I just wanted you to see it, a text file so you can see what I'm talking about here. That's file processing, and what I was talking about is database. And it does all these things we've talked about. Mainly, it keeps the data consistent. Another important thing about databases is it reduces redundancy if it's designed well. And this is what they're talking about here, duplicated data or redundancy. And you can see in a file system, normally you would keep all the information for the instructor in the file because why would you want to go to another book to find it? On a database, we have a separate file, and we don't keep the instructor data over here, just the identifying key, if you will, primary key, which is instructor ID. We store that in the schedule classes so that if we want to know we want to know more information about the instructor, we take this data field and use it as a key to look into this file, and then we pull that information in, we combine the information from the two, and then we display it as if they were all the same as in a file system. Now the advantages are a couple. Instructor changes their name. There's a basketball player plays for the Lakers his name is now World Peace, Meta World Peace, I'm sorry. So if he was an instructor here and he changed his name, we have to change it here, we have to change it here, and who knows where else it is. We have to find out where it is. And imagine if these were all in notebooks, and change his name in all those places. In a database, I change it in one place. The next time you look at this record, it's updated. That's the concept. That's the idea. It's a basic idea. Here's some different databases you can buy. Access is Microsoft, comes with certain versions of Microsoft Office. Informix is a pretty big one. IBM bought them. They own it now. Ingress used to be a big one on Unix systems, and it's still around. MySQL used to be free, I believe, but it's not anymore. Oracle purchased it, and they charge for it. SQL Server is actually what we use on the Adobe Connect server. We use SQL Server, I think we're using 2008. There's now a 2012, but we're using 8. And the SQL, we'll talk about that in a minute. And that's what we use. So you can see you can buy different databases. Each of these have a different approach, can have a different approach to databases. Most of the databases today are relational databases, and we'll talk about that in a minute. When you're designing a database, talked a little about this earlier, you have to have a data dictionary. And you develop a data dictionary. It's just like it sounds. You have each field name, data type for each field, and a definition in the data dictionary. Why do you do that? Well, you do it, as we talked about earlier, so you can actually decide how to structure your database. But it's also all systems analysis and design for technology revolves around the people that are going to use the system, or the people using the current system, and the people that will be using the future system. I, as a systems analyst, don't know what their business does, don't know what their data is. I can guess, but I really don't know, and it's not my job to know. It's my job to document it, and the people I interview and the people I talk to, the documents I look at, tell me. And what you run into often is politics. Who owns that data? Who has the right to update it? There's a lot of issues there, and it's not my job to decide those issues. It's my job to bring them on the table and let somebody else decide. But I have to bring it on the table. I have to create a data dictionary. Then we go through it. You probably don't want them to look at this, but you have a document of some kind where you go through and talk about it. And of course, as you get good at it, 85% of the time, you don't need to talk about anything. But there's a few of them you realize are going to be political, and you need to talk about it. The security on the system, the accuracy of the data, and other issues. And in fact, the success of the system depends on you resolving those issues before you finish your system. If you've got political issues that you can't solve, your system is going to have the same problems, and whoever's unhappy is going to make sure your system doesn't work. That's the way this stuff works. You can't just say, well, it's a program, we'll put it in, we'll deal with it later. That's not the way you do systems analysis and design. You get people to deal with their issues up front before you spend time and money buying hardware, developing software, and then all of a sudden the politics rears its head again. That's what a good systems analyst does. And we'll talk more about that when we talk about development. But that's what this is. It's a tool. You also put in here synonyms. Some people call it the account number. Some people call it the employee number. Some people call it the payroll number. And so you put those synonyms in the dictionary, because in most databases these days you can have synonyms. So if somebody calls it that, you can still retrieve the correct field, correct data. That's another, and data type and so forth. You can also, in more modern databases, put edit checks edit checks in there, like the range. We only want this number to be from 1 to 100. And if somebody keys 101, you'll get an error from the database. And then the data dictionary becomes something called a schema, which then becomes the database and so forth. But that's all we're going to talk about that. Tools, these are used to get information out of the database. And probably most of you have used something like this at work. It may be a screen, which would be a form. It may be something that you put parameters into. I want everybody that had a score of 40 to 70 on the last test. I want all people that were born in December. Whatever it is, that's what a report generator does for you. A query language, simple English-like. And then, of course, there's a program which interprets the query language and turns it into machine instructions, which are passed on to the DBMS. Just to go back and talk about how we access the hard disk and how dumb the computer is. But we create query languages so human beings don't have to talk zeros and ones to the computer. I don't speak binary. I'm sure you don't either. So we need a query language. I don't want it to be complicated. I want it to be as close to English as I can get. And query by example is a step further. And you just type in the data you're looking for into a field or the ranges, and it takes care of the query language itself. And here's a wizard, or a query by example, if you will. You select, and this is from Microsoft Access, I'm pretty sure. It doesn't say that, but it looks like it. So you say, I want a certain database. It gives you the available, then you have to select the table. Table's another term for file. And we'll talk about that in a second. So you selected, they don't show it here, but you selected the student file. It shows you what fields. You then tell it, I want these fields to be in my report. And then you take the next step, which is a title and a couple other things, and then you actually run the report. Okay, so these three fields are displayed here. Okay? And then you can take this a step further. A query by example would be, I only want people whose last name starts with H, whose first name is Robert, you know, that kind of thing. And that would be another step in here. And that's available too in Access. Down here is the query language. Well, you didn't have to write that. Access created it for you. But you can see how that works. Select these three fields from student. That's pretty clear. Okay. A form, well, you've all seen these. Whenever you go to the ATM to get money or to put money in your account, that's a form. And it just allows you to type the data, and then it does things in the background for you. Accesses the database. Report generator, query by example or something, and then it just prints out a report for you. Or it puts it on the screen, more likely. Another part of DBMS is the security. Who has access to do what? And we want to give people the least security level, or privilege as they call it here, that allows them to do their job. Some people might be allowed, and it's back to the same thing, add, modify, delete, or update, some people would call that. That's all you can do. So who can add new people? And that's probably only here on campus. There's only one department that can do that. That would be the registrar. Distance Ed can't add a student. Registrar has to do it. So if you call us and say, I'm not in your database, we have to tell you normally to call the registrar. And the registrar has to make sure you're in there. Maybe it's the wrong account number or something. But anyhow, least privilege. We don't have the privilege of adding students to the New Mexico Tech database. We cannot even update your record. We cannot do that. All we can do is read your record. We actually read your data from the registrar's part of the database and put it into our own database, which isn't really great practice. It's poor design, but there were reasons for that. Having access was an issue, so we just did it that way. So all we can do is read data in the registrar's office. Other people might be able to update. For instance, I don't know who, but me. Oh, I know, payroll could probably update records. Or when you pay your fees, there's the accounting department can update payroll or update student records to show you've paid and so forth and so on. But they can't add a student. They can modify your records. They cannot delete you. Nobody can delete you but the registrar. You get the idea. That's security. That's important in the database. It also does these things. Backup. And of course, recovery is when you crash and you take your backup and recreate your database. That's a recovery. And a log, real quick, database management systems keep a track of every transaction that hits the database. There's a lot of strategies for this, but here's the concept. Inside a log, there's a transaction that shows the before and after image. If your computer blows up, you lose your database, well, you have a complete backup of your database at some point. You do it once a week, once a month, whatever it is, once a day. And then you can take that, and that has to be offsite, not on your main computer. And you do that electronically, put it in the cloud. We talked about that in storage. And then if you lose your data, and remember, you're processing tons of stuff. Imagine Amazon, all their sales data and all the information you're doing online, and that's all going in. And they don't back up their computer every second. They back it up once a day or once a week, whatever it is. So all those transactions that happen during the day would be lost if they lost their computer. Well, but it's not lost because they put all the transactions in a log on another computer, and it's a before and after image of everything. So if you start at the bottom and work your way back from a full backup, you can recreate the state of your database when it crashed. Okay? And if that's a little quick, that's okay. Don't worry too much about it. Post something in the portal and we'll talk about it. I just wanted to cover that concept. And here's another picture of what I was talking about earlier. Maybe you can see it a little better here. Here's the data. Here's the index. And you can see here, here's the disk location, or the row number as we were talking about earlier, but this is the location on your disk drive, disk address. It probably wouldn't be these numbers, but that's okay, don't worry about that. And over here's the employee number, and this file's sorted by employee number. But over here, it's all out of whack in terms of the employee number. That's fine. You want to find employee 3, you read the index file, small file, you can keep it in RAM, it's quick. And you found, there it is, it's location 300, it's Shah Rakesh. Okay? When you add somebody new, well, the system's going to automatically give them 7 as an employee number. It's the next available one. And just by accident, it puts them in here. Bob Higginbotham. Okay? So the disk location is, might be 899. Doesn't matter. These don't necessarily go in order. And he's here, 7. You get the idea. This never gets sorted, never gets moved around. You just put the new one at the bottom. And of course, you may at some point delete this record. And then somebody, years from now gets 3 down here at the bottom. Well, if that happens, you got to resort. And there's also algorithms that if I don't find the key here, I go look at the bottom and blah, 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 blah. Anyhow, you get the idea. It's a conceptual thing I want you to get. Here's a picture of something that helps in design, and I think it might help you understand how the databases are actually stored on the disk. This is called an ERD, Entity Relationship Diagram, and what you have is entities. A university is an entity. These are things, people. Things that operate on your data or are responsible for the data. This is people. Not always people. A department's not really a person. You get the idea. But you don't store a department in here. You just you have a concept of a department. And the data, of course, you have information about the department, where they're located, phone number, so forth and so on. But you don't want to store any more information than just specifically about the department here. Instead, you create a relationship with other entities. Let's start at the top. Universities, New Mexico Tech, has colleges. Okay? So it's one university, New Mexico Tech, has many colleges, and that would be what we call here College of Engineering, College of Mathematics, College of English. Whether we have them all or not, you get the idea. One university, many colleges. Well, each college has, and that diamond is the relationship definition. One college has one dean. Okay? Each college has, one college has many departments. College of Engineering has mechanical engineering, electrical engineering, materials engineering, and so forth and so on. One college has many departments. Each department has a chair and has many professors, one to many, and one to one chair. It's interesting, though, that we can store the chairman inside the professor file and define it just by the pointers. In other words, we have one record in the professor file for Dr. Warren Ostergen. He's the chair for mechanical engineering right now. He's a professor also. If we want to find out who the chair is, we have a pointer in the department record that's labeled chair, and that goes over here and pulls Warren's record. If we want to find out all our professors, he'll also come up as a professor. And it's nothing in this field that tells, in this table, this file, that tells us that. There's fields over here that have pointers. If there is no chair, that field will be empty. And when we ask the database, it'll say there is no chair because it's empty. You get the idea. Then we're using the pointers we talked about in the index file located in this record to tell us these relationships. Okay? So one department has many students. And you might wonder, are we going to put a record for each student in here? Well, usually you don't. That would be too inefficient. You put the first student address here, And then the student has what we call a chain, but that's getting a little bit beyond this discussion. You get the idea. Inherent in the relationship, or the pointers, or the address in the index, is the relationship. So one department has many students. One student has many sections it's registered for, many to many. Many students register for many sections. One department has many courses, one to many. One course has many sections. So Math 252 has many sections, and then the section has its own identification. One professor teaches many sections. The professor doesn't teach a course. Okay? Thinking of that data index idea, I've just taken it another level, and the index is often stored in the department, university, college, wherever it needs to be, which defines that relationship. So that's a modern database. It's a little confusing. If you want to talk about it, let me know. We'll talk about it. This is the most widely used model of database, relational, because it's so easy to use and restructure. The way the data is stored is not as important as it was many years ago. You spent days, weeks designing exactly how physically your data got stored. It used to be really something, the whole process of actually figuring out how to store data. You don't have to worry about that quite as much. Relational database concept's been around since the 1930s. A guy by the name of Codd, I believe, developed some rules. First normal, second normal, I don't know how many normal. After about the third one, I get confused anyways, but don't worry about that. But unfortunately, because relational databases don't care about using RAM or processing or storage, they care about how easy it is to use the data. And the rule is zero redundancy is what you try to get to. That's what normal forms are about. The systems couldn't handle it. Memory was too expensive. Storage was too expensive. Processors were too slow to do everything that he designed. Well, it was a great design. It hung around, and then about 20 years ago, we started using it because the computers caught up. And just terminology, a relational database has tables. Another term. You can think of this as a file. Codd just used the term table, and it's what we use. SQL, structured query language, is designed to work with a relational database. We looked at SQL, and we'll look at it again here in a second. So you can think of a table as a file. These are the different tables. And inside the table, there's rows. That's probably better for you than records. Each table has rows. Again, think of a spreadsheet. And there's a primary key in each row. So that's one of the rules of relational database. There has to be a primary key. Primary means only one row has that value. Okay, so that would be your social security number. I know there's more than one person with some social security numbers, but that's not legally possible. So we pretend it's not possible. Each column has a unique name. And by the way, another phrase you'll hear that Codd used, which we really don't use, is tuple. How about that one? So each column is a field, or a tuple, as Codd called it. Or we often talk about it as an attribute. A car has what attributes? Oh, no, we would say a vehicle has what attributes? Well, it moves. It can move around in space. It has access points. Do all cars have 4 doors? No. Do they all have 2 doors? No. Some of them have 1. Do all vehicles have 4 wheels? No. We have a subclass car, which has 4 vehicles. We have another subclass motorcycle, so forth and so on. But for the purposes of this discussion, we have fields or attributes. Attributes of an instructor are what? Name, address, and so forth. You can see here, extension, that's the phone number, what an office number, their web address. Those are attributes describing instructors, or fields, or tuples. Then we define a relationship. Well, you can see here, the diagram we looked at earlier, the entity relationship diagram, would tell us how we need to link these up. And you can do this interactively with Microsoft Access in most databases. You just click on one and then click on how you want to link it up. And notice the student ID is in this record. And then there's codes that tie these together. And that's the relationship. Don't worry too much about this. This is getting a little complicated. I just want you to be exposed to this stuff. And so you realize how data is used. Some engineer developed software that allows us to do this. So when you enter your information on Amazon, it all goes into the database appropriately or is retrieved appropriately and shows on the web. And now you have some idea what's going on behind the curtain. Here is a SQL statement, a query, if you will. You would call that a query. And you kind of got to start in the middle here. From. Well, that tells us which tables we're going to use or which files. Schedule of classes and class catalog. Okay, now we know the tables. So you need to know those names unless you have that report by example we looked at earlier. And this is what Access will create is this statement. And I want these two tables to be joined, it's called, into one entity that only exists for this report, and then it goes away. It's temporary. And I want those two to be joined together into one table where the schedule of class, that's the table, this table, dot, see the dot? Class code, that's the field or attribute, equals the table class catalog, this one, dot class code. Notice they use the same name in both tables, that's okay. So in other words, I want the same section. What that means, they're same class. And where they're equal, we've got these two tables, and where the one field's class code is equal in these two tables, combine them, or join them into one table. Then I'm saying, select the class title, okay? That's the field I want. That would be this field. Class code, they kind of made a mistake and labeled this section, but it's class code. And this is the interesting thing about relational databases. And remember I told you earlier, you never want to store results in your table. So as the database is extracting the data, you're saying subtract a field called maximum enrollment, and subtract from it, that's the minus sign, the current enrollment. And make that a temporary field called seats remaining, which only exists while this query is being run by the database. And that's, of course, how many seats do I have left for that to register? And then give me a report. So this data, just to be clear, does not exist in the database. It's computed by the database management system based on your SQL statement. Okay? Pretty powerful stuff. You'll probably never have to do this because even if you pull data from a database, you'll be using query by example or some, fourth generation, they call it, or fifth generation interface, where you just say, I want to know what seats remaining are, and somebody else has already defined the queries for you. But I just wanted you to get a little background. Object-oriented database, of course, is used on the web frequently. Google Maps does not store the maps in their database. We don't store our recordings in our database. They're stored separately, and then we keep pointers, and that's the same thing. That's what an object-oriented database. It's a little more than that, but for now, let's just talk about it that way. And here's an example. These maps are pulled up based on their objects that are pulled up and displayed. Data warehouse is a term you might hear, and every company now has a data warehouse. Great example of what we call data mining. I read about years ago, what they call data analytics now. I don't know whether it's John Deere, but a company that made tractors wanted to serve their customers better, and they had no idea how to do that. Well, I mean, they had a lot of ideas, but they wanted to go to their data and figure out something they didn't know. And the data analytics found a pattern. All their vehicles had to be repaired at a certain time. And they didn't even know that at this point. They just wore out. And so they did some analysis and found out a part they had never considered was wearing out after after so many years or something. And they redesigned that part, and all of a sudden they're serving their customers better. And it was based on information they didn't know until they analyzed their data warehouse. Okay, they had all the records of the maintenance and so forth, or people complaining, or people bringing back equipment, but they'd never tied it together until they analyzed the data. I've probably told you before, I did the customer relationship management system, or frequent shopper card for Furr's supermarket. And one of the things we found is a correlation between, I think I've told you this story before, between diapers and beer. Nothing we ever thought about, we didn't do anything with it, and I'll let you try to figure that one out. Okay, we all know everything you do on the web is database driven. Behind the scenes there's a database. This is clearly an object database, all these videos. Imagine the size of these things. Wow, all those videos. Designing a database, and I think I've talked about all those things. You can look through those, determine the relationships, and then of course, as I mentioned, get the politics cleared up before you do anything because it'll save money. The sooner you get decisions made in the project, the better. There's two main titles in a database for big corporations. Database analyst. So in big corporations, the systems analyst brings all the data requirements to the database analyst, and they design the database. Many smaller, mid-level companies don't have an analyst, so the systems analyst helps the database administrator. The database administrator is kind of like the janitor, if you will. Very skilled, highly paid, these people, by the way. That creates and maintains the data dictionary and the security and so forth. Monitors performance. Sometimes you have to shut the database down and rebuild the indexes or the keys just to get it quicker, just for efficiencies, and so forth and so on. Security, backups, recovery. That's what the administrator does. This is an analyst position. Those are jobs, your students might want to be interested, might want to pursue. And of course, all you need to know, really, most of us, is how to get data out of the database. How do I do that? Okay, I think we're done. Just as a summary, you separate the criteria you need to find the data from the data. Why? For the same reason we talked about in every other aspect of computers, efficiency. We cannot take the whole database and put it in RAM. We cannot go through the whole database one by one by one. We could. 750 million accounts. Those are active accounts, I think. There's also inactive accounts. And find what we're looking for sequentially. Well, that's ridiculous. That means you'd have to read, on average, half of 750 million. What is that? 375, I think? So you'd read 375 records to find one person, on average. The first one would just take you one read. The last one would take you 750 million. You know how that works. Average is in the middle somewhere. But if we move the primary key into an index, we can sort that in order, and now we can do algorithms. When we talk about programming languages we're going to talk, you're going to have to develop a binary search routine, or at least understand it. That's the major concept. We want the people, us, you, me, that use the database to not even be aware there's database here. That's the goal of all people that work with technology, is to be as transparent as possible. You should never have to hear the term server in a perfect world. You shouldn't even know what that means. What do you care? I have this thing here, I want my data. I don't care what you're doing back over here behind the curtain. Don't even bother me with that. We're bothering with it here because you're trying to get a background so you can communicate some of these things to your students and understand a little better when somebody comes in and says, we have to rebuild the index file, or we have to restructure our database, or how do you want to find that? Do you want to do it by name? And they tell you, well, that's difficult because there's a lot of Roberts. You'll understand what they're talking about. You'll understand why it takes longer to do certain things than others.